Hey everyone, and welcome back to the Logic Unlocked. Here is an equation that appears simple, but its appearance is a trap. We are not just going to solve it. We are going to dissect it and expose why common methods are insufficient. Before we begin, we must establish the constraints on our variables. This is not optional, it is fundamental. For the base of an exponential function, a must be a positive number. This is a standard definition. Now observe the left side of our main equation. A positive number a raised to any real power will always result in a positive value. Since the left side is equal to x, it logically follows that x must also be positive. These are our rules. We will proceed with this understanding. The standard approach for an unknown and an exponent is to take the logarithm of both sides. We will use the natural log. Using the power rule, we bring the exponent down, and here we reach a critical impasse. You cannot isolate x using elementary algebra. A polynomial term and a transcendental term cannot be combined. Standard algebra fails. When standard functions are not enough, we need a special tool. This problem requires the Lambert W function. The W function is defined by the problem it solves. If you can force an equation into the form z equals y times e to the y, the function wz gives you the solution for y. Our task is to transform our equation into this specific format. Let's start from our last valid step. First, we isolate the constant term ln a. Now, to deal with the mix of x squared and natural logarithm of x, we must express x squared in terms of natural logarithm of x. We start with the fundamental identity that x equals e to the ln of x. Squaring both sides gives us x squared equals e to the power of 2 times natural logarithm of x. This is the key insight. Now we substitute this new expression for x squared back into our equation. This gives us an equation entirely in terms of natural logarithm of x and its exponential, which can be rewritten like this. Observe carefully. We are very close to the Lambert form, ye to the y. The coefficient outside the exponential is the natural logarithm of x, but the term inside the exponent is negative 2 times the natural logarithm of x. They must be identical. We must force them to match. We accomplish this by multiplying the entire equation by 2. Now it is in the perfect form. Our y term is negative 2 times the natural logarithm of x. The entire right side now matches the ye to the y pattern. Our z term is negative 2 times the natural logarithm of a. With the equation in the correct form, we can apply the Lambert W function, which directly solves for the y term. Now we can finally isolate natural logarithm of x. To get our final answer for x, we exponentiate both sides, arriving at the exact analytical solution. An answer is not an understanding. We must ask, when is this solution valid? The answer lies in the domain of the Lambert W function. For the W function to produce a real number, its input, z, must be greater than or equal to negative 1 over e. In our solution, the input to the W function is this term, negative 2 times ln a. Therefore, our entire solution is contingent on this inequality being true. Solving for ln a requires dividing by negative 2, which flips the inequality sign. Exponentiating both sides reveals the critical threshold for a. This is the master condition that governs the number of solutions. Our algebra predicts that the number of solutions changes based on a. Let's visualize this by graphing the two sides of our original equation. Y1 changes a to the x squared and yx. First, the yellow line y is equal to x is our reference. We are looking for intersections with this line. Here is the red curve for a equals 1.5, which is greater than our critical value. As predicted, it grows too quickly and never intersects the line. 0 solutions. Next, the green curve for a equals our exact critical value of about 1/2024. It becomes perfectly tangent to the line at one single point. 1 solution. Now blue curve for a equals 1.1, a value between 1 and the critical value. The curve widens and cuts through the line twice. Two solutions, just as the algebra foretold. Finally, purple curve, for a equals 0.5, a value less than 1. The curve opens upwards and intersects the line exactly once. One solution, the visual evidence perfectly matches our rigorous derivation. So we can now state the complete story of this equation with full confidence. When a is between 0 and 1, there is one solution. When a is greater than 1, but less than the critical value, there are two solutions. At the precise critical value, there is one tangent solution, and if a exceeds this value, there are no real solutions. And there you have it, a seemingly simple problem that requires a sophisticated approach. By introducing the correct tool, visualizing the behavior, and rigorously interrogating the limits, we uncovered a complex and beautiful structure. Never trust the surface of a problem. The truth lies deeper. Thank you for joining me on this journey. If you enjoyed this exploration, please like, share, and subscribe for more insights into the world of mathematics.